Dr. Ali Kemal Uncu is also one of the leading faces in application of computer algebra in combinatorics, as far as I know, and he is very active in many conferences such as ACA. I know him from 2021 when I started joining Coventry University. He was joining University of Bath, and it was still COVID time. He posted a video of his travel, which I liked it, and I think some of you may look at it later and recall some memories of COVID time. Yeah, Dr. Uncu, you can go ahead. Thank you.
So I was just saying, like, thank you for such high praise. Like, I really appreciate. Today, although it's not going to be about combinatorics, today we will talk about optimization, about normal cones, and really happy to be here. Really great, and I want to really talk about like finding new applications to known algorithms. And I'm so happy that Amir Hashemi actually talked about Grosvenor basis. Right, so let's start. So this is joint work with Michael Mandelmeier, who was an optimization student, then became an engineer in Föst Alpine, the second largest steel melting plant. And they needed to check. They do a lot of like numerical checkings for optimizing these processes. And he saw something in his thesis that maybe we can do better using computer algebra, because they were using numeric methods and they were using algebraic geometric methods. I will talk about them a little bit. And we were able to do something nice. So I'm really happy that computer algebra in a different branch was able to apply to optimization. And this is what I really like. I'd like to get algorithms, learn them, and apply them to new frontiers. And for that, let's start with what I think an algorithm is. So it's the really Babylonian way of thinking. I really like it. It is that you have a mathematical problem. You cannot solve it directly, but you're thinking in Babylonian times. You don't care about the proofs or anything yet. You just say, okay, what if we calculate things in such and such way? You give a finite amount of rules, saying that I want to calculate this and see where it goes. So create evidence, create more knowledge about the problem. And it's a really good way of like approaching things. And that is, I mean, slightly different than my previous pure math background, but I mean, I really enjoy it nowadays. It really helps me a lot to push the pure math as well. And the next thing is about future algorithms. So I want to thank Amir again. So this is a really nice conference. I really enjoyed the idea. I didn't know it the first year. I'm so happy to be here in the second year. I hope there will be many more of these future algorithm conferences. So going further, what about the future of algorithms? So I already mentioned that I think any algorithm, any process that helps you calculate something creates many frontiers, many new windows to do more research. So one thing is, can we get a better algorithm? Can we understand the complexity of the algorithm? And for me, more precisely, okay, so this algorithm was prepared for this one problem. Can we change it and use it in a different problem? And there are many examples of that. So thankfully, Hashemi's like talk mentioned these, that if you stay only in the elimination context, like polynomial elimination, you have many algorithms. So Euclid's algorithm, then you move on to Buchberger's algorithm, then you move on to like faster algorithms and Buchberger's, like F4, F5. So there's tons of algorithms that are doing polynomial elimination. But then there are tons of mathematical problems that you can reduce to polynomial elimination and use these algorithms. So I really enjoy like this connection between, I mean, different frontiers. And yeah, there are still questions about like the complexity of like the Grosvenor basis calculations in some domains. Okay, so moving on to our problem today. I want to talk about what quantifier elimination is. It's not polynomial, it's polynomial elimination, but I mean, it's not the same way. For the quantifier elimination, what you take in is a Tarski formula. So you get an expression with many polynomials in many variables. All of these polynomials related to 0 with some relation. It can be equal. So if they're all equal, then you're in the world of Grosvenor basis and everything. But it doesn't have to be. It can be inequalities as well. And for the Tarski, you need the coefficients to be in Z. But I mean, you can take it in rational values in general. And this formula is connected by many ands and ors and many like logical symbols like that. For what we say is the Tarski formula is, so any set that is defined by a Tarski formula, we call it semi-algebraic. I will use this word. So it just means that they're polynomials that define the boundaries of this. And we can have quantifiers on this formula. So there can be many quantifiers on top of this formula that we can try to understand. One example is this. So is there exists an x such that ax squared plus bx plus c is equal to 0? I'm sure you can solve it, but there is even more. So we know we can theoretically solve it. So Tarski actually said that these problems are decidable. So if you have this quantified formula, you can find theoretically, you can find an quantifier-free formula that explains the same set, that expresses the same set. And for us, we know this. This is a quadratic formula. This would have a solution 0 as long as the discriminant is positive, or the first coefficient is 0, so you have a linear, and b is non-negative, so you would cut the x-axis at some point, or if everything is 0. Right? So we can, if I forgot a solution, don't tell me, but I mean, everything here, there is actually, I mean, that you can get rid of this quantifier, get rid of that variable as well, and solve it and eliminate this quantifier. So that's what we mean by quantifier elimination. Okay, so this was an easy question, fine. How about this next guy? What if you have this? So for all epsilon, there exists delta, so there's some limit definition going on. Then for all x and y, such and such happens, implies such and such else, some new thing happens. It's quite hard, right? I mean, so this is not so easy to eliminate. Although theoretically, Tarski says that we can. And for that, we have our first major algorithm by Collins, which is called cylindrical algebraic decomposition, and it is also the name of the algebraic object. So algebraic object is also called the CAD, and what it does is it splits your space into multiple disconnected sets in a certain way, in a cylindrical way, so that you can check every cell and then decide if you have a solution, what the solution sets are supposed to be, and so on and so forth. Okay, so this is really what I said. It's just like you split your space in the highly structured set. So here's an example. If you have this polynomial, x squared plus y squared minus 1. So this is the polynomial. We may be looking for a relation. So this is positive, this is negative, whatever. So you take your x squared plus y squared minus 1 equals to 0 curve. Then you look at the projections. So maybe project it onto the x-axis and see where it cuts your x-axis. And once you're done with these cut points, then you lift it back to the y-axis and see where you have other important points, which changes this whole R2 space with infinitely many points into 13 cells, basically. So there's one cell, everything that happens below -1 is what's happening below -1 for this curve. So maybe this is less than 0, less than 1, whatever that is. And you can represent this whole cell with a single sample point. Or you can have 3 possibilities here. So there can be like things underneath. So there's one sample point. There are the things when we really cut the x-axis at this vertical tangent. And then there's another cell. Everything on this ray can be represented by this one point, and so on and so forth. So you just split your R squared into 13 different cells. And by cylindric, we mean that the projection onto the x-axis here, they are all either the same point or they're disjoint. So this projection of this and the projection of that are disjoint, right? And by calculating the CAD, by calculating the cylindrical algebraic decomposition for a Tarski formula, you can actually solve any quantified formula. Because you have a quantified formula, let's say, on this structured set, then by checking these sample points, you would know if that formula is satisfied or not. And if it is satisfied, you can just give the definition of this one cell using the polynomials that define its boundaries. And so it's a semi-algebraic set. So this is what quantifier elimination is. This is what CAD is. And I should say that there are multiple schemes to calculate a CAD. And it's an ongoing research project that I also contribute here and there to see if we can lower the complexity of CAD calculations. And it's really important because the complexity right now, as we know it, and I mean, as we know it, is that it's double exponential complexity. So it can go really bad. It is believed to be single exponential for most of the problems, but for really bad examples, that Davenport and Heinz showed, that it is double exponential complexity. And you need to take a lot of intersections of the polynomials to find these important cut points. That's the reason why you get double exponential complexity, right? The places where the curves like turn is important, where two polynomials intersect are important. So this is really where you get these, bad complexities. Okay. And I have to say that this is a complete solution. So if you can calculate the cylindrical algebraic decomposition, if you can calculate CAD for any given problem, you can solve that problem completely. And you can change the quantifiers of the problem and you would solve it too. You can change the relations of the problem, you would solve it too. Because you're really splitting the space that you have, into multiple separate small pieces. That gives you the essence of all the cells of where the things can change. But it's really expensive, so it's double exponentially expensive. There are cheaper methods for some number of problems. So if your problem is purely existential, like if you only have existential quantifiers, like so you want to know if there is a solution, or if there's a single solution, maybe there might be infinitely many, then they're incomplete, but many cheaper methods, and they go under satisfiability modulo theories. Okay, so if you have an existential problem, so it is better to check the SMT theories first to see if you can actually solve it that way. If not, CAD is a backup solution. It is expensive, but it would solve your problem. With asterisks, if you can calculate it. Okay, let's move on to the optimization. Let's move on to my collaborators, research. So my collaborator was trying to do these optimization problems, and sometimes they were failing to calculate like some important derivatives to see if they have a maximum or minimum, an extremal point for them. So in those certain situations, they tend to go to a set mapped function, set valued function, which is called the normal cone, and they try to calculate that. And even they were failing to calculate this thing. So what he said, well, we have this definition, which is some inner products of V star versus that x minus this centralized center point is supposed to be less than, at least asymptotically less than some differences in a certain set, in our constraint set. Can we calculate it if this set is semi-algebraic? Because for most of the parts, they say, like he said, that we take a semi-algebraic set anyway. So he said, okay, we have multiple possibilities, and I will show an example in a second, that we have an objective function that we want to minimize or maximize, and we have a set that we want to maximize or minimize this in, and by playing with that, we can actually take this set to be semi-algebraic. In those certain situations, can we calculate this? Can we find the normal cone? Because that would give us the answer. And what is a normal cone? So intuitively, it is really the directions that you should not go to keep optimality. So for example, if you're in this domain omega, it's a point, it is that getting out of this domain is not going to give you any optimality. You want to stay in the domain that is the domain of the problem. So on the inside, there will always be points around that might satisfy optimality. On the outside, on the boundary, which is where the things are important, you want to identify the points that you don't want to go to so that you can keep the optimality. So you look at the normal lines, like the perpendicular lines, and then you get this set mapped, the set valued map. So at this point, it is the set. At any other point, it's these rays, right? So this is really intuitively what normal cone is. It is just that all the directions at a given point, which I showed at x bar, that you shouldn't go to keep the possibility of optimality. If you get out of the problem, then it cannot be optimal anyway. Okay. So, for example, this guy. So you want to take this function, minimize the x plus y. That's the function that you would like to minimize. That is your target function. And here's the omega. It is the subject to these bounds. So that's the boundary of the set. The classic approach that we learn in calculus is, because it has multivariate, is the Lagrangians. You just do Lagrange multiplication. It tells you the direction that you have the best chance of optimality. So it gives you the direction where you should go to either minimize or maximize this problem. And in general, for other problems, I mean, also not necessarily like directly there that you can take the Lagrangian, these are called the KKT conditions. And these conditions can fail. So, and I will tell you that. Please take a second to look at this. What about the normal cone of this following curve, this omega, at the 0 point? What do you think is the normal cone of this point? It's not so easy, right? So if you think about the normal cones coming here, you take this ray. If you think about the normal, like the normal cones, which are the lines, the rays coming here, you will get the positive y-axis. So what will be the normal cone of this? And I can even tell you what the Lagrangian is. Lagrangian is take the derivative of x with respect to x, then plug in 0, so it's 1. The y value, take the derivative of this with respect to y, plug in 0, so it's 1. So it says the direction is 1, 1. So I shouldn't be going in the direction negative to that. So this point, negative 1, 1, should be in the normal cone. But if you only look at the KKT conditions, you don't even see that. You only see these two rays, positive and negative, like y-axis. So if you look at what we try to solve with the quantifiers, so instead, yeah, this is what I said. So the Lagrangians here. Then here's the tangent cones that you can calculate, which is the negative x-axis. Then you don't even see that the 1, 1 is in the normal cone. That negative 1 is in the normal cone. That violates the optimality. But instead, if you look at the definition that is given, so we said the normal cone suggests that negative y-axis and positive y-axis are the normals. Tangent cone says that this red line should be in the normal cone. And this is the negative Lagrangian, which should be in the normal cone, which the KKT conditions fail to find. Instead, you can look at the quantified formula. This is the same formula that was in the definition, written openly in a quantified way. Instead, if you can solve this, then it would give you this shaded blue area, which is the whole normal cone for this 1 point. So all the directions where if you go in that direction, you would violate the optimality. Wonderful, but I mean, can we solve it, right? So there are 3 quantifiers. So for all epsilon, there exists delta. For all x and y, this thing is going to happen. Well, unfortunately, you cannot just put it in a machine and like solve it. This is not going to work out. This will never terminate. This will not terminate, at least for like a week, which is what I tried. Okay, so we need to find better solutions, better ways of solving these things. So remember, this was the definition, which we turned into that. And we take our C to be semi-algebraic. And we need to find ways, find algorithms to actually split this in a reasonable way so that we can calculate these things. One thing that we can do, for example, is if you remember the whole definition, I was only focusing on this part when I look at that quantified formula. If you look at the whole definition, it also has the condition that the point that you calculate the normal cone must be in the set, must be in the semi-algebraic set, which is not reflected here. So one thing that we can do is we can directly just add it in. Oh, so yeah, if you only have one variable, so this was the example of that. If you only have one variable, this is the half positive x-axis, like the positive real line, then the normal cone can be calculated, no problem. And if you calculate that, you see that it becomes like this quantified free formula. And in this, we saw that this x bar being less than 0 appears, which is not important to us because I need that x bar where I calculate normal cone to be in the set. So it needs to be greater or equal than 0. And this gave us the idea that we are not using this condition, although we should, So can we actually add this into our calculations and make the calculations even simpler? And we can. You can add this condition where x bar is in the C. So this was one of the main, one of the early algorithms that we have. And you can then look at your quantified formula, and it would solve it even faster. And it's even better that this variable is not quantified. Of course it's not, because once we get rid of these variables, I shouldn't be seeing that variable anyway, if that is quantified. So one thing that you can do is you can directly take it inside the quantifiers and impose these conditions into your problem. So restrict your set even more. So this is maybe a more expensive CAD calculation on the inside, but you will eliminate many more sets. Okay. Again, still going back to this problem, can we solve it? Can we put the conditions here, like of what these things are, and then hop them in? Can we still solve it? The answer is still no, unfortunately, even though it is like two-dimensional. So we should do something even more smart. But before that, let's directly ask, like, what can be asked? What can we solve? We can try to solve three different things. We can say, okay, I want to find the full normal cone. Wherever that x bar is in the set C or omega, whichever you call it, can we calculate that? And that involves 3n plus 2 variables, which for a double exponential set, this is too much. But we did it for like a single dimension, right? So for 2 dimensions even, this is too much. 2 to the 2 to the 5 is like way too high sometimes. So we can then ask the real question, which is like what the optimization problems usually need, that you have a cusp point that you KKT conditions fail, but you still want to understand the optimality at that cusp point. So given a fixed point, can we solve, find the normal cones? So because you fixed n dimensions of your space, you have 2n plus 2 points. Still hard, but we can solve it. And the next thing is you can actually sample. You can say, okay, I think this point is important. Would the V stars, whatever these conditions are they in my normal cone? So you can just plug that in, and it's an easier question. You can try that too. But we will focus on this one. So, and really quickly, I'll go over how we can solve it a little bit faster. So one thing that you can do is, here the algorithm basically says nothing new. One thing we can do is this variable hopping. So if you know that you're at a point x bar and you have its conditions, you can take that x bar and then use its conditions with your quantified formula. So this is the x bar condition and the quantified formulas. And if you can do quantified elimination, then you'll be fine. Now here's this and I will explain what that is. So if you already have the conditions on the x bar and you're hunting for conditions on the V star, what you can do is, okay, x bar can be in so many different places, in so many different boundaries of my space or inside of my space. Why don't I take them separately? Why don't I take one bound and try to solve this, another bound, try to solve that. And in each boundary, I learn a condition on the V star and I use it as a feedback loop almost. So I take it, I learn a condition on the V star, and I can use this condition on the V star in the next run if I want to. And that would actually eliminate a lot of simplify a lot of things for me. Right? So here you can take where x bar can be, and you can split this space into multiple places and then try to solve them. And at the end, the totality of the conditions would be all the conditions together on the V star, what defines the normal cones. Okay, so this is really what we do. So you can take this curve above, then the point 0, 0. So I'm really doing the CAD of the constraint set. I have the above curve, the point, and the curve below. And if we take those conditions and impose them, then we can solve this problem by just looking at 3 different cells of the constraint set. And it's really helpful because this above curve, for example, is one dimension is only one-dimensional. There's a relation between x and y. So you can hop it in and solve that on the inside, right? I mean, so it just gives you one more relation to play with. Here, x and y both 0, so you're even like you don't even need to deal with that. This you don't need to deal with that, and this one is already, I mean, just even gone. So another one, so on and so forth. So it really reduces that. But this is not all. It's even better that we were only using where that central point x bar can be in the set. Can we also use the second point that is in the set and use the CAD of that? And we can do that, and we can use it as a feedback loop. This is the next part where it is just saying that instead of looking at the whole set where x's can be, think about your set being split for the x's as well as the x bars where the centralized, and think about getting one condition for x in every single cell. So you can I'm also splitting the cell on the inside of the quantifier. So this needs some thinking. It is not just something that is not quantified, but x is quantified, and I'm trying to split it on the inside. So it requires some theorem and some proofs related to that. But with this, we can actually just solve in a simple single-dimensional way. And we needed to get in many discussions with the referees, like through this condition, because we're really splitting a set from the inside and then saying that the intersection of all these sets would be the same set. And you can do it in a larger logic if you add more quantifiers, but that is exactly the opposite of what we wanted to do. We wanted to have as little quantifiers as we can so that we can solve it. And we needed to give some proofs here, but you can still do it. And even better, you can take your smallest cell with the lowest dimension, solve it, get conditions for V star, feed it back to the problem. Now you learned something for V star, and it is not quantified, put it inside, solve it for the next cell, solve it for the next cell, and have this feedback loop and get everything like that. And with this approach, we believe we can solve any dimensions. We solved it all the way to 6 dimensions, to Coulomb friction. And remember that even in 2 dimensions, the crude algorithm was not solving anything. But we can now solve it to the largest problem that we know. So 6 dimensions. So when we have a total of 20 variables, 21 variables, and we believe we can solve it for like an indefinitely many like variables. We just need to do this feedback loop. And as a final thought, can we do better, right? And the answer has to be yes. Otherwise, I wouldn't ask it. The point is that we get a solution for V star for every cell that we solve it on the inside, and we can ask if for this new cell, for the next cell, can we get a new condition for these V stars? That is an existential problem. We can ask it in an SMT way. So we can split our set, start solving, and at each iteration we can say, okay, I have a new cell. Would this new cell possibly give me a new condition on the V stars? If the answer is yes, it can possibly give us a new condition, then we can pay the price. We can do the quantifier elimination, CAD, whatever system we have, and learn that condition. But if the cell says, no, they cannot, this cannot give you any new condition, then we can skip this cell. So not only that we can use this feedback loop, we can also learn what cells to skip with a cheaper method. And this gives us really huge computational savings. And this is like how we solve the six-dimensional problem, the largest problem that we have, which my collaborator wrote his thesis on over into a 2-second calculation. And with that, I just want to thank you. And that's really it. Thank you for your time. And here's the paper that just appeared. And yeah.
Thank you, Dr. Uncu, for the presentation. We are at the time, but the next speaker is not here, so we can have a few questions. If anyone from the audience has a question, can ask, otherwise I will go ahead. Anyone from the audience? Okay, so I think I have to go through these things with, well, okay, Alexander, Yusuf has a question. You can
No, go. I will ask afterward.
Okay.
Go.
So I think I have to go through these things in an in-person meeting when next time I see you, Dr. Uncu. But just to make sure that I understood correctly, so the savings that you are doing is by playing with the constraints, moving them around, and also skipping some cells. But what about trying to reduce the number of variables? Have you given any thought on that?
So
Is it
that's
possible to?
yes. So that's exactly what this FCIs do. So the first thing that you do is so the first thing that you do is here, I guess, that you take your constraint set, right? For example, this curve, this cusp, then you take its cells, and on this cell, you have one less variable for the X bar.
Oh, so you're using equational constraint kinds of thing, right?
Exactly.
Oh, okay,
Exactly.
okay.
So
Good.
this is the equational constraints, and then on the inside, if you do the cells and even do it in a smarter way with increasing dimensions, you use a lot of equational constraints, learn some conditions on V star. Then you feed it back. Now the V star has one less variable most likely. You have a larger dimensional cell, but V star became one less dimensional, so you kind of balance as you go.
Mhm.
So you really use equational constraints as much as you can in both ways.
Good. Yeah, thank you. Dr. Yosef.
Hi. So maybe a general question about CAD, and maybe also with application to what with calculating a normal cone. Does it make sense to use some symmetries? For example, when you do the cut, you choose the variables, the order variables. Can you use some? For example, if you rotated it, you'd have another equivalent. For example, here, yes, but also in your code, you'll have another equivalent formula at the end, right? Can you use these symmetries to increase the to make the algorithm better?
I'm sure it can be used, and you're completely right. I think the symmetries would simplify the problem a lot. We haven't dealt with that, but you're right. I mean, these problems have a lot of symmetries, and a cone has, it's in the name, so it's really a cone shape. We know that it's theoretically proven. A cone itself has symmetries as well. So I didn't try to impose that, but I mean, that might be the next thing to do, and most likely there are ways of just using these symmetries. So it's a really good suggestion. Thank you.
Thank you.
Okay, is there any other question? If not, we can thank the speaker again with this sticker of clapping.
Thank you.
Thank you, Dr. Uncu.